So the majority of physics is covered by actually mechanics. And for mechanics too, we skipped a certain, not that we skipped, it is not included in the AP1 physics class. There is hydrodynamics and hydrostatics, the mechanics of flowing fluids as well as the stationary fluid. We skipped that.
On the every physics test, did you like a free response? Is there a free response and multiple choice?
Multiple choice, I guess.
I think, yeah, for this one it's multiple choice.
Okay.
All of it's going to be multiple
Multiple
choice.
choice, and there won't be any like essay questions like no.
I don't think so. Not for physics.
Okay.
Yeah.
For AP2.
Yeah, AP 1 and 2. I don't think there's free response.
Okay.
Mostly just multiple choice.
You leave it out. Do you have his number?
I think Daniel does. Yes.
And vibrations. So what are waves? What does waves do?
Transport.
Transport
light,
what?
sound.
Yeah, transport energy from one place to another. So energy is transported from one place to another in the form of waves. Okay? So before we start talking about real waves,
Okay.
we first try to describe what simple harmonic motion is. Without considering the term simple first, let me tell you what harmonic motion is. What is harmonic? Harmonic. What does harmonic mean? Harmonic means that something is occurring repeatedly, again and again, again and again. So if something is occurring repeatedly with a similar time interval, we call it is an harmonic motion. If something which is on motion occurs within a same given time interval, we call it a simple harmonic motion. Harmonic motion. And there are various kinds of harmonic motions, complicated situations. The most simplest one is the simple harmonic motion. For example, why did I say the most simplest one is the simple harmonic motion? If something is occurring like this in a sinusoidal form, that's the simple harmonic motion. But the same thing can happen like this.
Wait, what's the example of something that isn't harmonic?
That isn't harmonic? Okay, I'll give you an example for harmonic. Then you can figure out which are not harmonic. Okay? So, those shapes, even this is harmonic. You get the same pattern, but it is not simple as the former one. Therefore, now you should be able to figure out that this motion is simple harmonic. Okay, so to understand what simple harmonic motion is, I'll give you an example. The motion of a simple pendulum. What is a simple pendulum?
Going back and forth.
Okay, so you can form a simple pendulum very easily. You take a ball or something. The best simple pendulum, the real simple pendulum is actually a cone-like object which is pointed at the end, hung by a certain length. So it can be any, it can be a ball or whatever, a paper ball or anything you want. And if you give it a small push, what would happen? This would go this way, comes back, goes back and comes up like this. Okay, then once again it will go this way, moves back and comes back. So you can see that this occurs repeatedly. And let's assume that nothing is causing this motion to stop. Then the motion of this can be represented as follows. Consider this. Let's take, consider this point as this x equals 0 point. Now when the pendulum is moving this way, when it is moving up, if you consider its projection, now it is moving like this in a curved path. But if you see its projection, what is a projection?
Projected,
It's
projected motion.
yeah, it's planar wave or it's aerial wave. It will be on a straight line. Do you understand that? So when the pendulum is moving from the x equals 0 point outwards, this will go this way. And when it stops, when the velocity becomes 0, it will come back this way. Okay? And it will go this way and come back to the same position. So, so this is an example for simple harmonic motion, simple pendulum. Tell me another one. Let's take a spring. Let's attach a spring horizontally.
What about a projectile?
A projectile is not simple harmonic.
So does it go back and forth?
Yeah, it doesn't. Okay, if it goes back and forth, suppose if you throw a ball up and it bounces back
Yeah.
and it reaches, if there is no energy dissipation at the
Yeah.
point of collision, then it will be simple harmonic motion. Okay? And take a spring and attach a certain mass at the end. And this is lying on the floor. And you give it a push, then what would happen? Yeah, this will move back and forth, back and forth. So that is also
It's like
simple
dribbling the
harmonic.
ball up and down.
Yeah, same way.
So what is,
It has to, but it has to come at the same, to the same
yeah,
level
Yeah.
to be simple harmonic
Yeah.
motion. Okay, so in your figure, sorry, in your note, you have similar example. This is the simple pendulum. This is the spring I was talking about, and another one. Take a rope or a string attached to 2 points, and you pull it up and release it. What would happen? It will move up and down, forming a wave. Okay.
so it's
So-
throwing like a baseball and then like it curves or something, but it just stops. You know, it doesn't go back and forth. That wouldn't be harmonic,
No,
right?
that is not harmonic. Okay. So what is happening here? The particle which was here is now here. Particle here is now here. Okay. So it will be here only for a short while. At the next moment, this will be above this, and this will be above this. So all the time there is a wave which is propagating forward and reflecting back, moving forward and reflecting back. Okay, so all the time the string won't show a waveform like this. It will change, but still it is simple harmonic because it occurs during same time intervals. Okay, so I spent too much time there. So now you know what's okay. So that is simple harmonic motion. But if you are to define simple harmonic motion, and this is how you define it. It is a type of periodic motion. I'll let you write. You just listen to me first. It is a type of period motion where the restoring force is directly proportional to the displacement in the opposite direction of the displacement. What is that? We talked about couple of weeks ago, not couple of weeks ago, 2 weeks ago. What's that?
Displacement.
The restoring force is directly proportional to the displacement.
So
What law is that?
Oh, the second.
Hooke's law.
Oh, Hooke's law.
Yeah, so in other words, simple harmonic motion occurs according to the Hooke's law.
Hmm.
Take the simple pendulum, that is the most easiest example. Let this go, consider its upward motion. When the simple pendulum is at this position, you can feel that it is always being pushed back. So that is a restoring force. So this restoring force is directly proportional to the distance between the initial position and the final position. So any periodic motion, anything which occurs repeatedly by a force which is directly proportional to the displacement, then such motions are considered as simple harmonic. Okay, so that is by definition. Can you write this down? Somewhere above. A type of periodic motion where the restoring force is directly proportional to the displacement in the opposite direction. Okay, so I have to spend too much time on now describing what simple harmonic motion, but still if you understood, that's it. Okay, so simple harmonic motion therefore can be represented using this equation according to Hooke's law. But its displacement is represented in a different way. If you read the next part of your note, you will see an equation, some useful formulas. xt equals a cos omega t plus psi. Psi, I call it psi. I don't know how you call it.
I haven't seen it before.
Yeah, that's how I'm used to call it. X equals a cos omega t plus whatever it is, psi. It's called psi. That's how I know it. So what does this mean? Consider a circular motion. If the particle is here, where would its vertical projection be? It will be here. When the particle is here, its vertical projection will be here. Now when it is here, it's here. And when it compacts, you can see it coming back in the same opposite direction towards the origin. And then it passes the center when it is here, and when it comes down, it will be here and back and forth. So what is it? So the circular motion is in a way a simple harmonic motion. Circular motion too can be considered as a simple, it is not a simple harmonic motion but can be considered as a simple harmonic motion. Okay, so it goes up and down. Consider the position of a certain point of this circular path, and if this moves in omega angular velocity, its displacement, let's consider this direction. You can consider either directions. Its displacement in this direction will be, if this is r and if this is theta, x would be r cos theta. Do you understand that? Okay. Then I'm going to erase r and replace it with a. If you consider the maximum displacement of this simple harmonic motion is a, that is the radius. So this will always be radius wherever it is. So I call it A, because I'm going to call it amplitude later. at a later time. I'm going to call it amplitude at a later time. I'll tell you what it is later. So if it x equals a cos theta. Now I'm going to give something else for theta. We don't know what theta is. Let's use some known terms to represent theta. Theta is the displacement, the angular displacement. We know omega equals theta over t. So if the time taken by the particle to move from here to here is t, then theta can be written as omega into t. Do you understand it? Omega t. Now do you understand how we got this equation? But in addition to that, we have another term. We call it the phase shift. The phase shift. Phase means, that means it is the angular shift. So at the moment, I'm not going to describe it a lot because it can confuse you, the concept. Assume that this was somewhere here initially, before it started its simple harmonic motion. Then it would represent this angle in another way. So it can be sometimes it can be a negative value, sometimes it can be a positive value. Suppose it was here, suppose it started from here, Siddhant, then your omega t would be this part. If this angle is, if this is omega t and if this angle is psi, then this would be psi plus omega t. You understand? So if it is in the other way, it is the negative component of it. Okay, so just assume that this has to do with the initial position of the simple harmonic motion. Okay. Then there are some other formulas that you need to know, which we have done before. What are they? Omega equals 2 phi f. We did it under circular motion. Omega equals 2 phi f. Then we know f equals 1 over t. Therefore, we can simply convert the above equation into omega equals 2 phi over t. Or in other words, omega means angular displacement over time. Time for one circle, in other words. You should be able to remember these equations and turn one from the other. Then you get another equation for a spring and mass system. Did we talk about this before? No, yes. So for a spring and mass system, omega equals square root of k over m, whereas m is the mass and k is the spring constant. Got it? Then if omega equals square root of k over m, omega means 2 pi over t. That means square root k over m. So if you, according to the necessity or according to the question, you can simply interchange these terms. Then finally you have f equals, it is actually 1 over t, it is not simple t over t, it's a small mistake. F equals either 1 over capital T or t equals 1 over f. Got it? Okay, we have 3 sums. Actually it is one sum in which you have 3 subdivisions. And oscillating system. Okay, what is oscillations? What are oscillations?
Circle?
Yeah, the circular motions, the repeated circular motions that we have been talking so far. So in an oscillating system, it is created by releasing an object from a maximum displacement of 0.2 meters. The object makes 60 complete oscillations in 1 minute. Determine the object's angular frequency. What is meant by angular frequency, Siddhant?
How fast is going?
Angular frequency is actually omega.
Okay.
Frequency is f, angular frequency is considered as omega. So omega
55F.
is 2 pi f. So there is a certain clue to find f. What is it?
Displacement is 0.2.
Yeah, no, not the displacement. Displacement has got nothing to do with the frequency.
Oh, 60 complete
Yeah,
displacement.
there are 60 complete oscillations in 1 minute. So what is actually frequency? Number of oscillations per second. So if
So
there are
one.
60 oscillations, yeah, that's right. So
So omega is 2 pi.
T, T is 1.
Yeah.
That means F is also 1. Got it?
Yeah, so it's 2
So
pi.
it's 2 pi. Omega equals 2 pi. So that's the answer for the first one. Write it down. Then comes the second. Determine the object from the previous question's position at t equals 10 seconds. Now is the time to use the equation that I was talking about, the equation I derived. What is it? You should know it by heart. X equals a cos omega t plus psi. Okay. I was telling you about a capital A, and for capital A, I told that I'm going to describe it as amplitude in the future. And when I introduced you capital A, I said that it makes the maximum displacement, it forms the maximum displacement.
Yeah.
Okay, so in the question it says that the object is released from a maximum displacement. So 0.2 meters is the maximum possible displacement that oscillatory system can make. So A is 0.2 meters cos omega, we have found it already.
2 pi.
Yes. T is
10.
how much? 10.
20 pi.
And psi, no clue is given for psi, so we can forget it. Okay?
So
X will be 0.2 cos
20 pi.
20 pi. So you can either use the calculator and find the value for the cos of this angle and get the final answer. So let's leave it as is. You can do the calculation. Determine the time at which the object is at 0.1 displacement. Now what should you do, Siddha?
Solve for
Solve for
t.
t. That means so what is the formula that you should make use of? This one. Yeah. This is the typical formula for any simple harmonic motion. So now you need to know the displacement. Oh no, you need to know the time. So you already know the displacement 0.1.
I have 0.1 cosine 2 pi t, and I need to solve for t.
Yes. A is 0.2 cos omega is 2 pi t. So you divide, this would become half.
Wait, would it be 0.1?
0.1, this is 0.2.
I thought displacement is the amplitude.
No. Displacement is not the amplitude always. Amplitude is the maximum displacement.
Oh.
In the third question, it is just one possible displacement. It doesn't mean that it is the maximum. Maximum is always a constant.
Okay.
It won't exceed 0.2 meters. So this would become half. So cos 2 pi t. So half means sine, the angle would be, half means when the angle is 60. Isn't it? So this will be 2 pi t would be 60 degrees. So t will be 60 means in 2 pi,
So
in
30
radians it
35.
would be how much?
T divided t equals 35.
Yeah, now we can convert. Now this is in radians.
Yeah.
This is in degrees. Let's convert this into the radians, that's the easiest.
Okay.
Oh, okay, let's convert it into, no, radians would be much better. 60 means, 2 pi means 360, 2 pi divided by 6 means 1/3. 60 means 1/3, yeah. Pi over 3, this would be 2 pi. So it will be 1/6 of a second. Got it? So even without the calculator, and if you are fast, you can simply find this answer. Alright, let's go to the next step. So under the second objective, we will be talking about the relationship between the frequency, the angular frequency, and period. So we'll be talking about this in terms of questions. Read the first one.
If a kg block is attached to a 200 Newton spring,
Newton per meter spring. What does that mean? What is that?
The force that it can apply?
Force per a kind of a length. So what is it?
Meters.
The spring constant.
Of the
F, yeah, F, remember, F equals Kx. So K would be F over X. So the units would be Newton per meter.
Okay.
So that's simply the spring constant that they are talking about.
Okay.
They don't mention it, but you should know it by the units.
Okay.
Yeah, keep moving.
As shown is displaced at a distance of 8 centimeters from its equilibrium position before being released. Determine the period of oscillation frequency and angular frequency for the block.
Yeah, okay. So some of the data may not be necessary for our question. Okay, so you need to know, you need to find capital T, simple F. So if you know capital T, it is just a matter of few seconds to find the frequency and angular frequency omega. So all these three are interconnected. So what do we have? We have the mass of the block. We have the spring constant. If you turn to the first page, Siddhant, you will see that omega is equal to square root of k over m. Omega is equal to square root of k over m. Did you see that?
Yeah.
So k is 2000, mass is 5. This makes that it is 400 square root
So 20.
20, omega equals 20 rad per second. So that's omega, the angular frequency. So if you know the angular frequency, how do you find F? Omega equals 2 pi F. So F would be omega equals 2 pi. Omega means 20. 2 pi would be 10 over pi. That's the frequency. Then what would be the
F equals 10.
10
pi.
would be pi over 10 seconds. So Siddhant, in this question they ask for the period of oscillation first.
Yeah.
But the data provided allowed us to find the angular frequency first. It's okay. Sometimes they change the order to confuse you. That's fine.
Okay.
So you don't need to find an answer from top to the bottom. You can even find answers from bottom to top. Okay, let's move on to the next one. Let's spend a couple of minutes on this. I want you to do this now. Rank the following horizontal spring block oscillators. The system of oscillating system is called an oscillator. Okay, resting on frictionless surface. Why do we consider frictionless? That means that no external force is retarding the motion of the spring. So that it will be simple harmonic motion, simple harmonic for a longer period. Got it? In terms of their period from longest to shortest. Okay. Now we are going to analyze this using their period. What is period? Which letter denotes the period? Period. Period means the periodic time.
Okay, T.
T. Periodic time or period of oscillation or period.
So
All mean the same.
We use it.
Find T.
We use a.
What do we have? We have the mass and the spring constant. Using the mass and the spring constant, we are able to find what? We are able to find
T.
not directly.
We can find F.
Not directly. What do we find using K and M? Omega.
Oh.
Yeah. So first you find omega.
And then we equal that to 2 pi
Yes.
F. And
Yeah.
then-
Yeah. You don't even have to equal that. Now, Siddhant, your questions will mostly be MCQ, multiple choice. So what you will be doing is you will be eliminating answers. So sometimes you may not need to find the exact answers. What we are going to do is we are going to rank this. We are going to put them into a certain order. For that, it is not a must to find the final answer. We should take shortcuts. I'll tell you how. Now omega, what's the relationship between omega and T, Siddhant? Omega means 2 pi over T. So omega is inversely proportional to capital T. So larger the omega is, smaller will be
T.
T. Okay, so we do not need to calculate T. Find omega as soon as possible. Turn to that. Yeah, find omega for this. Omega will be square root of K over M. Right for each.
Okay.
Yeah, okay. Okay, I will also find with you. A. Omega will be square root of K over M. So this would be 100, that means 10. B would be square root of 50 over 7. So I would say that this will be approximately equal to square root of 7. 49 divided by, 7 into 9 is, wait a minute. Yeah, 7 into 7 is 49. So you will get 1, 7. Okay, let's go to the third one. Omega would be 2000.
I got 100.
Hmm?
Wait, what's wrong?
Are you using the calculator?
I just square root of 1000. I don't think it has a square root.
Okay, you use the calculator and get the answers. Or where did you get stuck?
No, I didn't get stuck. I just found out.
Okay, you can use the calculator and get the answers, and I'm not using the calculator.
Okay.
I'm using it by myself. So let's use both ways. 2000 divided by 2. 1000. So this will be 1000. 1000 will be 100 into 10. 10 square root of 10. D would be omega equals 1000 over 5. So this will be 200. 200 will be
Okay.
100 into 10 root 2. Okay? Alright. So did you find the order?
Yeah, I got the same ones. I know.
Yes.
Number
So,
B is 2.67. C
so
is
how much would this be? 2.67.
67. C is 31.622.
C is 31.
110 is
Yes. And this would be a little bit less. Okay, so what I did was, Siddhant, without making use of the calculator, what I did was, these are the, I want you to know these two. I want you to think critically and not always use the calculator, because sometimes this method saves time. This is 10, this is root 7, this is 10 root 10, this is 10 root 2. Obviously out of these three, this is 10 into 1. 10 root 2 means it is something more than 3. So obviously this is going to be larger than this. And this is going to be in between these two. Alright? And then square root of 7. 7 means it should be, 7 is between 3, 4 and 9. So it should be 2 point something. So this would be the smallest. B would be the smallest. Do you
Don't we have
understand?
to find the time now?
Hmm?
Do we have to find the time now?
No, you don't have to find the time now. Okay, now let's rank them. B is the smallest. Then comes 10. A. Then comes D. And then comes C, the last one. And change the order.
What?
I told you omega is inversely proportional to T.
Oh, okay.
Larger the omega is, smaller would be T. So we are going to rank from the longest to the shortest.
So it's
So the longest would be,
B.
this is the smallest,
Yeah.
this
so
has the smallest
very
omega,
longest.
this would have the largest. So time wise, it would have the same order. No, B would be the largest, A would be the next.
U would be smallest.
Yes. Got it?
Mm.
So don't waste time without trying to find time. This critical thinking is very important in physics. Alright, let's go to the next one. So the next topic is determine the total energy of an object undergoing simple harmonic motion and sketch graphs of kinetic and potential energies as functions of time or displacement. Actually this, okay. Alright, now let's come. This is the spring mass system lying on a frictionless surface. Okay, and we give it a small push or you press it, and then if that the starting point will be its equilibrium position, then it will move this way and will move this way too, and back and forth. Okay, now if this is A, if this is B, and if this is C, how would you, if this distance is x is done, how would you describe this x? It would be in the opposite direction, therefore I would call it negative x. Okay, right, now I am going to describe displacement, velocity, potential energy, kinetic energy, force, acceleration for each of these places. Now let's go to, I'm not going to write anything. You have the note with you, so you follow the note. Displacement A. Okay, never mind, I'll write. Displacement A, B, C. Okay, A is the equilibrium position. So at A, the displacement would be 0. B, it would be x, and by C, it would be negative x. Got it? Okay, velocity. By this place, what can you tell about the velocity of the particle? It stops here because it's not moving anymore.
So
It has no velocity.
Okay.
So by B and also by C, velocity would be 0. And that suggests that you would get the maximum possible velocity at A. Got it?
Because it's moving.
Because it's moving. That suggests that potential and kinetic Okay, let's talk about the kinetic energy.
You got A.
A would be max. This would be
None.
0, 0. Of course, this is not the gravitational potential energy that we are talking about. It's the elastic potential energy. So, when the kinetic energy is at its max, this would be
0.
0 at its minimum. And when this is 0, it is converted completely into the elastic potential energy. So, max. Got it? Okay, so according to the definition of the simple harmonic motion, can you tell where would the mass of this mass spring system would experience the maximum force?
A.
No. By the time it reaches this point, it is experiencing, it really wants to go back. Like we are moving leaving away, we are moving to some other place from home. And we always want to go back home. That's how it is.
But wouldn't it
Yeah,
have
this is the
Max-
particle's home is A. So he's kind of being attracted or being forced.
wouldn't it have the most acceleration on A?
Wait, I'm coming to that. Okay, so the restoring force on the particle would be at B. The maximum possible restoring force. Okay, force will be max at B and C. Okay, so at B, why is it negative? Why in the diagram it says that it's negative? Force is a vector quantity. Displacement is measured in this direction, but the force is in the opposite direction. Therefore, you need to use a negative sign for this. Whereas for the other one, though the displacement is negative, the force is in the positive direction. Therefore, it is positive. Then, where would you experience an acceleration? According to Newton's second law, you would experience an acceleration if there is a force acting on it.
Yeah.
So maximum, if using F equals ma, when F equals max, A would also be at its maximum position. So this is 0, this is 0, negative max, positive max, acceleration. Got it? Okay, so if you draw a graph for this, let's take potential energy, kinetic. This is the 0 point. Kinetic energy is at its max and potential energy is at its 0. So it will be like this. Got it? So this is potential m of kx squared. So it will be actually it will not be a straight line. It will be a curved line. Why do I say that it would be a curved line? Because elastic potential energy is half kx squared. So each time x is increased by 1, it is being squared. Therefore, it won't get a linear relationship. It will get a parabolic. Okay, so you can draw this. This is a very common. So this is the total. This is the total energy. So this will be the elastic potential energy, and this will be kinetic. This is a very common graph. I have seen this in questions. They give you different kinds of shapes. What they do is they interchange the names and they interchange the shape too, and they ask you to find the
What is
correct.
straight right now on the top?
That is the total energy. Total energy would be always the same.
Combined,
Yeah, it is constant according to the conservation of energy. Okay, let's move on to the next sum. A 2 kg block is attached to a spring. A force of 20 newtons stretches the spring to a displacement of 50 centimeters. Fine, so and so and so. Okay, let's start. Okay, let's start with that. Find the spring constant. How do you find what are the equations with the spring where you get the spring
N
constant?
divided by M.
F equals kx, energy equals half kx squared. Okay, so those are the two equations. So keep them in mind. And omega equals also square root of k over m. But we are not talking about any angular frequency. So let's discard that. First one. Okay, I'm going to draw this and write the relevant data so that it makes me feel comfortable with the sum. I always do that.
Wait, so should we draw it? Draw it?
Yeah. When you draw and write your data in a diagram, Siddhant, it makes us it has almost done half of the sum. Because otherwise we'll be thinking in our mind, we have a picture in our mind which is not actually permanent. It can fade things away.
It's very...
Yes. So I always suggest that you draw, even if it is a simple one, that you draw the diagram. Okay, spring constant K. F equals Kx. So K would be F over X. F equals 20, X equals 50. 50 means now we always should use the SI, the units. That means X would be 50. How do I convert this into meters? Divided by 100. That means into 10 to the power minus 2. Okay?
Oh,
Yeah. So remember those conversions, Siddhant. So things become very easy when you remember those. If you convert say millimeters into meters, what you should do is you must multiply it by 10 to the power negative 3. You divide it by 1000, that means you multiply it by 10 to the power negative 3. If you are converting centimeters into meters, that means you need to divide it by 100, that means you should multiply it by 10 to the power negative 2.
Oh, sorry, that's right.
Alright? Okay, so keeping that in mind, so this is 0, 2 over 5 means 0.4, and when this comes up, it becomes positive 2. So that makes it 40. And please make it a point to write the units. Total energy. How do you find the total energy? I just told you the equation.
The elastic potential with which
half
energy.
K x squared. Because we have already found K. So you can make use of it. K would be 40, X would be 50 into 10 to the power minus 2 squared. Okay, can you find the answer? This is 20. This will be 25. And 10 to the power minus 4. So 1, 2, 3, 25 into 2 is 50. 1, 2, 3, 4 would be, final answer would be 5. Am I correct?
I
Amaka, can you use the calculator and find the answer? Yeah, so it would be this.
Hundred?
100? Oh, let me see. 20, 2,500, 1, 2, 3, 25.
Wait, so 20 times 2,500.
3. This is, you have a square here.
Yeah, 50,000 times 20, 50,000 times 10 to the negative
50,000 times
4. 10 to the negative 4.
-4. That means 1, 2, 3, 4, 5. That's right, I'm right.
Yeah,
Five.
sorry, 5.
So it should be 5. Okay. The speed of the block at the equilibrium position. Okay, how do you find that? Speed of the block at the equilibrium position. Now think. We have no equation. Find the speed of the particle at the equilibrium position. But we know something. Energy is conserved. We know the elastic potential energy at the maximum position.
Yeah.
And that elastic potential energy is converted into kinetic energy at the equilibrium position.
Okay.
Okay? So, kinetic energy would be 5. Okay? Now, we do it. And
So 1/2 times 2 kgs. 25. So 25.
is it 25?
Go 1/2.
5. M equals 2.
And then goes to yeah.
So, V squared would be 5.
Yeah.
V squared would be 5. So, V would be
Oh yeah, that.
square root of 5.
Yeah, that'd be screwed.
Okay? So, if you know the square root of 5, you could have written it. I think you should know the square roots. 2, 3, 5, 7.
Yeah.
I think you should know them. Never mind. Speed of the block at x equals 30 centimeters. Speed of the block at x equals 30 centimeters. Now think about it.
It's like B.
How do you do that? Now this is at 50.
Yeah.
If this is 0, this is 50.
30.
Now this is 30. Now we are talking everything in terms of energy. Now we are at a midpoint. What do we have? What is the energy that this particle is experiencing?
Acceleration.
What kind of energy would this particle be experiencing at 30?
Okay, kinetic energy.
Not only the kinetic energy, something else too. Elastic potential energy. It is halfway through.
Gaining it.
Yeah.
Okay.
So, the elastic potential energy that the mass had at this point is now is in the process of converting into kinetic energy.
Great.
Okay, so at this point it has both elastic potential energy as well as kinetic energy. So total energy would be how much? What is the total energy? Wherever it is. Now at this point the total energy was 5.
Yeah.
It was completely elastic potential. At this point the total energy was 5. It was completely kinetic. So even at this point the total energy would be 5, and that is a combination of half kx squared and half mv squared. Got it? So let's take half. K is how much? 40. What is the distance? What is the distance?
30.
Distance is 30. So 30 squared plus half m is 2 and we need to find b squared. Okay, so a matter of simplification, but let's do it. So I would have taken this half out. Siddharth? I would have taken this half out
Yeah.
and cross multiplied it by 5.
Okay.
So it becomes 10. 40, then I have 30 squared. 30 squared means 2
900.
zeros, 9. 900 into 40 would be 36
36,000.
and 3 zeros. Plus, I have already taken this 2 out. So this would be 2v squared. Oh. This is 30 centimeters. Now, I was wondering, I got stuck here. Why? It's good that I got stuck. I forgot to convert this into,
Oh, 0.0
I forgot to convert this into
meters.
meters. That made me think, how? Now this is uncomparable. These two values are uncomparable. That is what made me think that I have gone wrong somewhere. So learn the things from what we do. So this would be, how much did we get, Siddharth, for this? 36,000.
Yeah.
Oh no, it should be 40.
20,000.
Yes, 36,000. So 36,000 means 3 zeros. Now you get 4, negative 4. 1, 2, 3, 4 should be 3.6.
Yeah.
Got it? And this would be 2v squared. So when you take this out, this will be 9.4 divided by 2v squared. Am I correct?
9.4.
Not 9 point. Sorry. 6.4.
6.4.
6.4.
Yeah.
6.4.
So,
Yes, 6.4. That
square
means
root of
v squared would be 3.2. So v would be how much?
1.7888.
1.7?
8888.
Yes, okay. So I will make it 1.79. I will round it off. ms minus 1. Got it? So you can do the same thing when the block is at x equals negative 40. Nothing would, it will be the same. So there won't be any change. There won't be any change from the negative sign. Why is that? Because it's a
Isn't it
square.
turning from elastic potential to kinetic energy at that state? Isn't it turning from elastic potential to kinetic energy?
Yes.
Yeah.
Yeah, it is actually turning from elastic potential energy to kinetic
same
energy.
equation.
Yeah, this is the same equation, though the displacement is negative. It is going to be squared. So that negativity has got nothing to do with the answer. Okay? Right. So can you do it by yourself?
Yeah.
Okay, so I will skip that. Then I'm going to,
Do that at home?
yes, you do it at home. Because I have some more to do. Now, I am moving on to the 7. The magnitude of acceleration at x equals 50 centimeters. Okay, so how do you find the acceleration? This is a 7. F equals m, sorry, m
Over
a.
time.
So acceleration would be
Mass
mass.
divided by
Force
c
is,
squared.
okay, when the displacement is 50, the force exerted on the particle was 20. It's given in the question at the beginning. So F equals, A would be F over M, F would be 20, M would be how much? M would be
22 kg.
2 kg. Yeah, so that would be 10 minus 2. Got it? So this 50 had nothing to do with the final answer. But that 50 suggested that F equals 20. F is not 20 all the time. the net force at x equals 25 centimeters. The net force at x equals 25, oh no, that is a tricky question. A net force at x equals 25. How do you find that? How do you find that?
So we would have to find the force applied from C to A. And then the force from A to 20.
F, okay. Let's use F equals Kx. We know the spring constant.
Yeah.
That's 40. Now we know where we are. It's 25 into 10 to the power minus 2. So the net force at 25 is 45 into 25 into 4 is 100, 1000, 1000 divided by 100 is 10. So you can see at the maximum position the force was 20 and it has halved by the half the distance. Last one, the position where the KE is equal to PE.
Maybe the
Where KE
middle of
is
AC and middle of AB.
We'll see. Position where actually the diagram was like this. This was the diagram. The position. This is the position. This is the position that they are talking about. So, how do we think about that? Okay. I hope I have enough space to do it. So, when potential energy is equal to kinetic energy, half mv squared should be equals to half kx squared. Okay. So, half get cancelled. M is how much? 2. I'm not sure whether I'm going to get the answer from this. I'm trying because I too got stuck here. 2 v squared. Then k is how much? 40. And x squared. So this is v squared equals 20x squared. So when in terms of x, so this is the relationship between x and v when the two potential energies are equal. So v would be 20, sorry, square root of 2 root 5 into x. So as far as I know and as far as I can figure out, I will stop my answer like this. I would say that the two energies would become equal when v equals 2.5 times square root of 5 times x.
Okay.
Yes. Because I have no other clue. Okay. Shall we move on to the next one?
Yeah.
Analyze the simple harmonic motion of an ideal pendulum. So what is an ideal pendulum, Chitra? Ideal pendulum means there are no external forces acting on the pendulum. Everything is perfect. There is no air resistance. The string is smooth. There is nothing. No reaction will be acting on the pendulum from the spring. Everything is smooth. So that is the ideal situation. So in an ideal situation, the period of oscillation of a simple pendulum can be denoted by this equation. If this is the simple pendulum and if this is the length of the simple pendulum, usually you count it up to here. And if you consider it as a small one, if the pendulum is very small, you usually stop it here. Okay, so T would be 2 pi square root of L over G. This is a standard equation. For a simple pendulum, if it is in ideal conditions, the period of oscillation would be T equals 2 pi square root of L over G. That is not given in the text. Write it down and square it. And this equation is also true if you give a very small push to the pendulum. Now I have done this practical with my students before, and we have seen that this is actually not exactly correct when you push it back a lot and let it move. You should give a very small oscillation, a small angle. This is actually true for a very small. And when you do this lab work, you should actually at least have a length of about 1 meter or 1.5 meters to get the proper relationship. You get for the others, but when you do it practically, you need to have about 1 meter length. That is just for your information. Okay, so the next is, so angular frequency. Okay, angular frequency. What would be the frequency? T. So if T so what would be F? What would be F? F would be upside down 1 over 2 pi square root of G over L. Okay, Sita, look here. So 2 pi F would be square root of G over L. 2 pi F is, in other words, angular velocity or angular frequency. So angular frequency would be square root of G over L. But if you know this by heart, you can simplify the others. The displacement of the pendulum from the equilibrium position is also a sinusoid, like the spring block system. I talked about this before with you. And the displacement of x, or it means the vertical or the horizontal component of the displacement with respect to time. That is what is denoted by t. I hope you know this. What does this mean? X is a function of t. That means x is dependent on time. So x equals a cos omega t plus psi, or it can also be written as a sine omega t plus psi. Why is it like this? If you take if you take this angle as omega t, and if you take this distance, it would be a cos omega t. If you take this distance, still it is simple harmonic motion. It would be a sine omega t. So
everything in different angles.
Yeah. So it depends on the question of what to use. Most probably,
Cosine.
yeah. So what we usually do is the cosine equation. But if you need to use the sine equation, they would let you know. Okay? So you don't worry about it. Let's go to the first question. A grandfather clock is designed such that each swing, that means each swing means half a period, of its pendulum takes 1 second. What does that mean? So T by 2 equals 1. Therefore T means how much? 2. T equals 2. How long is the pendulum in a grandfather's clock? In grandfather clock. So T equals 2 pi square root of L over G. If T equals 2, this is 2 pi. L, G is 10. That's a universal constant. So 2 get cancelled. And this would be square root of L would be 10 over pi. L would be 100 over pi square, if I didn't make a mistake. Okay, Sita? What is the period of a grandfather's clock on the moon? Okay. Where the acceleration due to gravity on the surface is around 1/6 of that on the earth. Okay, so sit down. Now here, what I'm going to do is, I already know period of oscillation on the earth. Now, this sum suggests me, this is a kind of a comparison. So if this is T earth would be 2 pi square root of L over G earth. If this is T moon, this would be 2 pi square root of L over G moon. G moon. I'm going to divide this. If I divide this, all the common terms are cancelled. So what is the comparison between E and M? The ratio between Earth and Moon, the periods of Earth and Moon would be equals to square root of Gm. Now Gm goes up and Ge goes down. Te is 2 seconds. We found it. We don't know what Tm is. We know when compared to, if this is G, this is G by C. Sorry, G by 6. Then G get cancelled. What do you get here? 1 over 6. I think I'm correct. Yes. Yeah. Yes. So, finally, Tn would be 2 square root of 6. I hope I'm correct. Yes. Do you get that?
Yeah.
Okay. Now let's do the next one.
Okay.
Rank the following pendulums of uniform mass density from highest to the lowest. Okay, so that, what does that mean? Uniform mass density, that it is made out of the same material. But you can see in the figure, they have different shapes. One is very small and the size, the shape increases. But what are we going to do? We are going to rank
High to low frequency. The small.
frequency, F.
The small to how it's fastest.
Yeah.
Mm.
So, first of all, would the shape or the mass contribute to the frequency?
Yeah.
Nope. T equals 2 pi square root of L over G. So if you form a simple pendulum of the same length but with two different material that have two different masses, you might think that their period of oscillations would be different, but it is not. Even this is light and even this is heavy, both would be oscillating in the same period of oscillation, in the same frequency. Got it?
Yeah.
Okay, so we need to actually, so what does that mean? So T, what is T? T equals, okay, T equals 2 pi square root of L over G. We need to do, we need to rank it using the frequency.
Yeah.
That is omega or F. So T equals 1 over F, 2 pi square root of L over G. 2 pi is a constant, G is a constant. So what does that mean? Frequency is inversely proportional to the square root of the length.
What's the longer?
Yeah, so yeah. So the longer the length of the pendulum is, smaller would be the frequency. Okay, so we need to start it from the highest. So when the frequency is highest, the length should be smallest.
So it would be A.
A. Then what is the smallest one? It should be A. Yeah, I'm sorry. WA, then comes WD, then comes WB, and then comes W.
C.
Do you want to break it down?
Oh yeah, schedule one.
Okay, so the next sum is the period of an ideal pendulum is T. If the mass of the pendulum is tripled while its length is quadrupled, what is the new period of the pendulum? Okay, think, Siddha. What does it say? The mass of the pendulum is tripled, length is quadrupled. Would there be any change from the tripling of the mass?
No.
No. Okay, let's write the equation. So let's forget about the mass. T equals 2 pi square root of L over G. Now what do? We are going to quadruple, we are going to make it multiplied by 4. The length becomes 4 times now. So this term becomes 4L now. So when this 4 comes out, it becomes 2. What does that mean? It is T is,
So then, this getting larger is getting smaller.
yeah, no, I want to know how many times by which it is
3
doubled.
times smaller.
Huh? 2 times doubled.
Yeah, 2 times double.
Yes, so this becomes 2 times 2 pi square root of L over G. So this was the former one. Initial one,
So
now it is
it's
doubled.
2t,
Yeah,
2t.
yeah, 2t, that's right. So you can write it's doubled. And put a star and write, tripling of the mass has no influence on the period of oscillation. Okay, next question. Which of the following are true for an ideal pendulum consisting of a mass oscillating back and forth on a light spring? The 4 answers are: the kinetic energy is always equal to the potential energy. Is it so? Would they be always equal?
No.
No, because it's always being interchanged. The kinetic energy becomes potential energy, and then potential energy is turning into kinetic energy. Yeah, little bit. So it is not, so put a put a cross there. Then the next one. The maximum force on the pendulum occurs when the pendulum has its maximum kinetic energy. Now go back to that table. Where do we get, when did I say that you would experience the maximum force? When it is, when you are away from home. Yeah, you want to go back home when you are away from home, so badly. So maximum force is exerted when you are at the top. That means when you have the potential energy, not the kinetic energy. So it's not. The tangential acceleration of the pendulum is 0 when the mass is at its lowest point. So when the mass is at its lowest point, that means it is in the equilibrium point. That is the point. When do you observe the maximum acceleration? When you are away from home. You get the maximum acceleration when you are subjected to the maximum force.
What does
That-
tangential?
Tangential means it's tangential. There's a spelling mistake here, a small mistake. Tangential means that now actually this is kind of a circular motion. Though this does not complete a circle, this is a kind of a circular motion. So this has a circular acceleration, not a linear acceleration. But at each point, it also have an instantaneous linear acceleration too. And that is tangent. You know what tangent is? In mathematics, you know what
Yeah.
tangent is. It is tangent to the circular motion here. That's why that instantaneous velocity is known as tangential velocity. Got it? So you get the maximum force when you are away from home. At the same time, you are being accelerated at a maximum level when you are away from home. So that is also wrong. Okay? Then finally, angular acceleration of the mass remain, yes. Angular acceleration would remain constant because you would see that this is moving, look at me, like this. So angularly, it is being constantly moving back and forth without any stop. Okay, next one. So I will do the next one and I would leave the next two sums for you to do at home. Because you also need to think. Alright, a pendulum of length 20 centimeters. A pendulum of length 20 centimeters and mass 1 kg is displaced at an angle of 10 degrees from the vertical. What is the maximum speed of the pendulum? Maximum speed of the pendulum. Maximum speed is obtained when it is displaced max. Okay, so the maximum displacement would be here. Okay, so I will mark this AB. I will write energy at A would be equal to energy at B. So what is the energy at A, Siddhant? Energy at A would be totally kinetic energy, half mv squared. I'm sorry, what I don't know, I think I said something wrong about velocity. Maximum velocity is obtained here, I'm sorry. EB would be potential energy, mgh. Got it? With respect to this point. So this is the height. So m get cancelled. So we need b squared, that is 2gh. So v would be square root of 2gh. So we know 2 and g, and so it's just a matter of finding h, which is difficult. Now look here. How do you find h? That is the verb. Now this total length is 20. I will draw an arrow too so that you will understand. This length is also 20. Okay. Then if I call this distance as x dash, what would be x dash, Siddhant? X dash would be 20
Movement.
cos 10.
Yeah.
Okay.
Goes back.
Yeah. So what would be simple h? Simple h would be 20 minus x dash. Do you understand? 20 minus x dash. So x dash would be 20 cos 10. So you can get the answer and substitute it here and get it. Alright. Next sum, I want you to do it at home, but I will give you a small hint. A pendulum of length 0.5 meters and mass 5 kg is displaced by an angle of 14 degrees from the vertical. A similar scenario. What is the speed of the pendulum when its angle from the vertical is 7? Now midway, Siddhant. Now midway. First of all, what you should do is, you should find the total energy. the total energy when it is displaced max, that means when it is at 14 degrees, then that total energy would be equal to the energy at the intermediate point. So the energy at the intermediate point would be potential energy plus kinetic energy. So potential energy can also be, that is mgh, that is simply mgh. So m we know, g we know, h can be found using the same method. So now you know the total energy is equals to mgh, you know how to find h, plus half mv square. Got it? So you do it at home.
Okay.
Next one you think. Okay? So I didn't give you any work. Define a pulse. Pulse is a single disturbance which carries energy through a medium or through space. Okay. Siddhant. Now can you see the displacement I formed by pushing this goes forward from here. So the whatever the first displacement I made is propagating forward. So a pulse is a displacement or a disturbance that you make, which would carry energy from one place to another. Okay, now you understand what a pulse is. Okay, go to the next page. So if that pulse is like this, in a couple of seconds, its next position would be this. Got it? If this is for the pulse initially, then after t times it would be here. After another time, it would be here. Okay? Then these pulses can reflect when they meet a boundary, when they meet an obstacle. If the obstacle is rough, Siddhant, the pulse, when it is reflected, now this is the pulse which is moving towards the obstacle. If the surface is rough, it would invert when it is going back. Got it? It would be inverted. But if the boundary is soft or smooth, and if there is no friction, then it would not triple, it would not invert. It would move back in the same shape.
Okay.
Got it? So draw this. This is forward, but remember Siddhant, this is the same figure. This one should superimpose on the other one.
Okay.
So this is the rough surface, this is the smooth surface.
Just reflects.
Yeah, it reflects. Remember the shape. Okay. Now I'm coming to the velocity of waves. Now you know what a wave is. And a wave is represented by a sinusoidal form. If this wave propagates forwards in v velocity and the frequency of the wave is f, v equals f lambda, where lambda is described as the distance between similar occurrences. Similar occurrences. So lambda means either the distance from a crest to crest or trough to trough. Okay? Or even from here to here or here to here. That's what I say. Lambda is the distance between similar occurrences. Okay, so V equals F lambda. Alright, now you know this equation. What is the difference between mechanical waves and electromagnetic waves? What are electromagnetic waves, Siddhant?
Sorry.
Did you draw this? Did you draw
I
it?
drew it.
Yeah. Okay. So what are mechanical waves? Mechanical waves are the waves that we form like this. You have one single motion which moves each particle on the medium up and down, or back and forth, back and forth. But electromagnetic waves are a different kind of a wave, electromagnetic waves. So in short, we call EM waves. There are two fields, one electric, other one magnetic, propagating, vibrating in two perpendicular directions, like this. Suppose this is my electrical field, this is my magnetic field. I don't know whether I will be able to do it. This is moving this way, this is moving, I can't. This is moving this way, while this is moving this way. But still, both of them are moving forward as a one. So there are, it's kind of a couple with different ideas, two different opposite ideas, but moving forward in life together. Okay. Okay. So I'll draw it. So if you have two colors, make use
Isn't
of
it
two
like the
colors.
EM spectrum? What you meant?
Yeah, I'm going to cover that one next. So, if this is electric, that means the particles are propagating like this. Okay, Siddha? Now I'm going to use a different color because I want to show that it is perpendicular. See? They have the same frequency. I forgot to tell you that. They have the same frequency. Their crests will be always on top of each other. Their troughs will be on top of each other.
What are crests and troughs?
Okay, crest is the top of a wave. Trough is
No.
the
About
trough. Okay, I thought that you knew it. But my blue color is not working very well. Okay?
Yeah.
Right. But still, both of these are moving forward in this. So this is the propagation of light. This is the direction of propagation. So this is moving this way, up and down. So it is perpendicular to the propagation of light. This is moving this way. Still it is perpendicular to the propagation of light. So there are three things happening at the same time. Three directions involved.
Yeah.
So this is the electromagnetic field. Okay, so I hope you got it. So electromagnetic field is, if you want to quickly write down, you say electromagnetic field is electric and magnetic fields oscillating in two perpendicular directions. While moving forward in a direction perpendicular to both. Okay, so did you, okay, right. So a brief summary of EM spectrum. Now Siddhant, since it's taking time, I am not going to draw the EM spectrum. Okay, so you go home and find out, Google and find out the EM spectrum. But I will tell you what it is. EM spectrum is, there is a wide range of waves in EM spectrum based on their frequency and wavelength. Basically based on their wavelength. So this is the visible light. you can draw the subdivisions. And this side is wait a minute. Is it infrared? Should be, oh, I missed it. Visible, this is infrared, IR, this is ultraviolet. Okay. So there are subdivisions here. So I'll give it as homework.
Okay.
But what you should know is, when it is going this way, frequency is increased and lambda is decreased.
And like radio, UV.
Sorry?
Like, and there's like radio waves. And
Yeah. So radio waves come here, I think. No. No, microwaves and radio waves, they come here.
Okay. Which one is like the most powerful?
You cannot
Gamma,
actually.
gamma, right?
Yeah, gamma. Gamma is this way. Gamma has the maximum frequency. Is at this point. While VLF, you may have heard VLF. Then you have UHF. Earlier in nowadays, the radio, the television waves were UHF, VHF. So
What do they stand for?
Huh?
What do they stand for?
Ultra high frequency, very low frequency. Okay, so now this is your homework. You draw the spectrum, find out what the subdivisions are. But what I want you to tell is, there are three components: visible light, ultraviolet, and infrared. In this side, frequency is the highest. When you go to this side, the frequency is the highest. And this is the lowest frequency, very low, that's why you get a VLF. And I also said lambda is lowest. So according to V equals F lambda, where frequency is increasing, and then if lambda is decreasing, then your velocity should be constant. So remember, the radiation is propagated in the speed of light. So there V equals C, which is equal to 3 to 10 to the power 8 in this one. Okay, the speed is the same, but depending on the frequency, their lambda can change. Okay, so I'm going to the next one. So now I told you what mechanical waves are and what electromagnetic waves are, and about the electromagnetic radiation and how the frequency increases and what the speed of electromagnetic radiation is. Now there are actually two subdivisions of mechanical waves. One is longitudinal. Longitudinal.
Which page are you on?
Here. After the pulse. I didn't go back much. Here, back here. Okay, that's fine. Longitudinal. Longitudinal means, sit down. Now what did I do? I pressed this. So you could see that these some parts were compressed and while some parts were stretched. So if you have certain particles and if they compress, and these are the depressed ones, these are the compressed ones. We call this part as compression, and the released ones or the stretched ones are called rarefactions. Rare, R-A-R-E, factions. That's the name for it. Okay. So the length between two compressions is lambda. So in other words, in longitudinal waves, the motion of the particles. The particle move in the direction of the wave propagation. The wave propagates in this direction and the particles too move in the particles vibrate. This particle is not going to move from here to here. It will still be here. Now when I gave this a push, did this one go down? No, it didn't. But it moved. It moved back and forth where it was. So what I was going to tell you was the particles move in the direction of the wave propagation. This is the direction the wave propagates. The particles also move back and forth in the same direction. Whereas in transverse, this particle is moving up and down, up and down. Got it? Now, after a couple of seconds, this will be down here. But still, your wave is moving forward. This is the propagation, direction of propagation. So, direction, this is the direction of propagation, and this is the particle motion. So, in transverse waves, particle moves in a direction perpendicular to the direction of wave propagation. That is already mentioned in the text. This is the crest, this is the trough, and this maximum displacement is the amplitude. Okay? Right, now we have a couple of questions. We won't take much time to answer those. Right. First one, which type of wave requires a material medium, something in the medium to travel through? Sound, television, radio, X-ray. Which one?
X-ray.
Okay. EM waves do not need a medium to travel. We know that solar rays are radiation.
Yeah.
So when light rays are coming from sun to the earth, it may go across lots and lots of vacuum spaces. So that tells us that EM waves do not need a medium to travel. So you write it down. EM needs no medium. It can move in a medium, but it is not a necessity. So television, radio, X-ray, they are EMs, but sound is not. So sound is a longitudinal waves, a longitudinal wave like this. Therefore, of course, it needs a certain material to move. Next one. As a transverse wave travels through a medium, the individual particles of the medium move. Transverse means opposite in the perpendicular. Perpendicular to the direction of wave travel, parallel to the direction of the wave travel, in circles, in ellipse. Which one? Huh? Yeah, first one. The diagram below represents a transverse wave. The distance between which two points identifies the amplitude of the wave?
DNA.
No, amplitude is half of that.
No, DNA.
You don't have DNA.
Or any.
A, that's right. Increase in the amplitude of a sound wave produces a sound wave. Okay, just for your information. Do you play any musical instrument?
I used to play trombone.
Okay, so have you ever tried on a keyboard?
Yeah, it wouldn't be higher pitch.
No. Play C.
Yeah.
If you play C on the keyboard, and if you play the higher C, you get two different sounds. and we call it pitch.
Yeah.
The frequency of vibration at 1C would be different from the frequency of vibration from any other note. So frequency decides on the pitch,
Okay.
and amplitude decides the loudness. Okay?
Okay.
Amplitude decides the loudness. Okay, next sum. Periodic wave having frequency of 5 Hz and a speed of 10 ms minus 1 has a wavelength of V equals F lambda. So you need to find the lambda. Lambda means V over F. V means 10. F means 5. Lambda is 2 meters. Next one. An EM wave traveling through a vacuum has a wavelength of 1.5 into 10 to the power minus 1. What is the period of this EM wave? Okay, so we have only, the only data we have is the wavelength, that is lambda. So, but I told you velocity of an EM wave is c. So, speed of light.
So I forgot that constant.
3 to 10 to the power 8. So V equals F lambda. So,
So 3 times 10 to the 8 divided by 1.5 times 10 to the 1.
yes, so lambda would be, let me see. Oh no, lambda, V divided by lambda would be F. V would be 3 into 10 to the power 8. Lambda would be 1.5 into 10 to the power minus 1. That would be F. And period would be the reciprocal of it.
Okay.
Okay, next one. A surfacing blue whale produces water wave crests having an amplitude of 1.2 meters every 0.4 seconds. If water waves travel at 4.5 meters per second, what is the wavelength of these waves?
So 4.5.
Yeah, V is 4.5.
Then F is what?
F,
0.4. Or
F is, T is 0.4.
yeah.
Every 0.4 seconds, that is T is
1.2
0.4.
divided by
F is 1 divided by 0.4.
So
So
0.3.
you can find the lambda.
Three. 1.5.
Yes. Okay. Now I want you to do the next sum by yourself. Okay. Yes, at home. And at the end of the sum, it says V of sound through air at STP. What do you mean by STP?
Standard temperature and pressure.
Standard temperature and pressure. So V of sound is given. Even you can take it for this sum too. Okay? Do this too. Understand how the principle of superposition is applied when two pulses meet. So that's easy, Siddharth. Suppose two pulses are meeting. This is one. And this one is the other. They will be added. Okay, and the final one would be the height of both. It will be like this, something like this. So, superposition of waves. Suppose it was on the other side. This would be very much less than this. Got it? Now keeping that in mind, go to the next, and this phenomena is called interference. What do you call it? Interference. Okay. Apply the principle of superposition to the phenomenon of interference. The diagram below shows two pulses of equal amplitude. A. Approaching each other along uniform string. When the two pulses meet at P, the vertical displacement of the string at P would be how much?
These two are A?
Yes.
It would just be 2A?
They are in the opposite direction.
Oh, 1/2.
Not even 1/2. 0. They cancels off.
Oh, they're heading up.
Up and down.
Oh, I thought.
Yeah.
Aren't they like conjoining?
Not conjoining. Yeah, they are conjoining, but when this is moving down,
Yeah.
this is being pulled up.
Oh, I thought they were
Yeah.
together.
Yes. Now do you understand? Next one. The diagram below represents two pulses approaching each other. Which diagram best represents the resultant pulse?
So is this one being pushed forward to the right?
Yeah, they are coming forward. They are meeting. They are colliding. So assume that they are coming on top of one another. Yeah, 2. Okay, so now we are I'm supposed to describe these two phenomena. Understand how resonance occurs. Do you know what resonance is?
Well, I know what resonance structures is in chemistry, but it's not.
Yeah, I can't remember what resonance structures are in
It's not
chemistry.
related, probably not. Right?
Yeah, I think. I don't know whether it has any resemblance. We'll see. When I describe, you will understand. Now suppose Siddhant, an airplane, is moving very close to our building. What would you think that would happen? What would you feel?
Shaking.
Yeah, you will see that the windows will rattle, there will be vibration on the walls. Okay? What is causing that?
Force.
When the airplane is moving, it is vibrating. Its machines are working and it's moving against wind pressure, so there is of course vibration. When it has velocity, so it's vibrating. So whatever the vibration it has is propagated through air and makes other objects to vibrate too. Alright? And if that vibration can cause the other objects to vibrate in its own natural frequency, then that is called resonance.
So like a massage
Yeah.
thing?
Yeah, similar to that.
Like,
So what is natural frequency? Now, each of us are different from one another. We have our own energies, our own capacities to move. Like if you will be more energetic when compared to me. Likewise, all the objects on the earth has its own frequency if it is given a certain force. So that is its natural frequency. So resonance is when an external force or external vibration causes another object to vibrate in its natural frequency, that is called resonance. So sometimes this resonance can be disastrous. For an example, if there are some now, assume something is, a swing is oscillating very fast, back and forth, back and forth, back and forth, and ultimately it can break and fall. So every object has a breaking point too, a breaking frequency too. So ultimately, if that resonance can lead the vibration of the other object to its breaking frequency, the other can collapse. For an example, I can tell you an example. I can't remember the place actually, but it happened somewhere in USA long time ago. Soldiers had been marching on a bridge, a suspension bridge, I suppose. I'm not sure whether it's a suspension bridge or not. They had been marching, so when you march, there is something vibration. It is periodic. There is a pattern in it. So that vibration had caused the bridge to oscillate in its own natural frequency.
and collapse?
And collapsed. So nowadays, after that incident, soldiers are not marching on bridges. They're not allowed to march on bridges, they walk. They usually. So I don't know whether they do it, they follow the same rule now, but that's how I
They probably have better suspension and everything now.
Yeah,
Infrastructure.
yeah, there may be.
Yeah.
As another one, a tornado or a cyclone can cause bridges to vibrate and fall down, collapse. So resonance is actually, that is the bad part of the resonance. There is a good part of resonance too. Musical instruments. Now take the violin.
The vibrations
Yeah.
give us
So
sound.
you, whatever, when you pluck the strings, that vibration goes inside the hollow box of the violin or the guitar and resonates the air inside in its natural frequency. And since it is a box, that it is being reflected back and forth and produces a nice sound. That is another example of resonance. There are so many examples. Suppose you take a glass of water and fill it up to a certain height with water and rub the surface. Have you seen some people rubbing the surfaces of glasses of water and producing musical sounds? Rubbing like
Yeah,
this
yeah,
and
yeah.
yeah. So that is also
Yeah, people
resonance.
like blowing on straws
Yeah,
and
yeah, that's
everything.
right. Even what is happening when you blow? Now you said that you play the trombone,
Yeah, yeah.
so there are also
The vibrations
yeah,
from the mouth.
yes,
Yeah.
that's right. That is turned into that resonates the air column.
Yeah, and then when you like tighten up and when you speed it up, it
Mhm.
goes higher. The pitch goes higher.
Yeah.
So,
Okay. So now you know that. Where is my note? Finally, so I can finish the last one. Apply the Doppler effect qualitatively to problems involving moving sources or moving observers. So if there are questions, they will be given next time. What is Doppler's effect? Have you heard of Doppler's effect?
Yeah, but I don't know what it is.
Where did you get, what have you heard about Doppler's effect?
in planets, the planets. I'm at
Yeah, Doppler's effect is used to find the speeds of planets too. Alright, we are standing here and we hear the sirens of an approaching ambulance. What would you feel? What would you say? What would you feel? You would you would hear that its frequency increases when it's coming closer, and when it moves away, its frequency decreases. So I'm a stationary observer, and the ambulance was a moving source of sound. So when there is relative motion between a source and an observer, either way, one stationary, the other moving towards you or moving away from you, or the source is stationary and I am moving towards it or moving away from it, or both are moving towards one another, or both are moving back and forth, there is relative motion between the source and the observer. Then what you hear is not the exact frequency. It would not be the real frequency of the siren. That is called the Doppler's effect. So it's this very same Doppler's effect that is used by the police officers to monitor, to find the speeds of fast moving vehicles. They emit a signal, and based on the reflection, the speed of the reflected wave, they can figure out, the machine calculates the speed of the moving vehicle. And another example, bats. You know bats can't see in the night.
So they like.
Yeah.
So they
So-
say something and like how far it rebounds.
Yeah.
They can judge the
Yes.
distance.
So it is an innate ability for them. They don't calculate anything. So when they move, when they fly, they hear sound and they hear it back. So based on the reflection, they can figure out whether they have obstacle in front of them. Okay? So that is
That's not.
Yeah, so if wave-wise, now if this is a sound source, these are the waves that it will be producing outwards in all directions. So if it is moving, these waves will be closer to one another. So this is the scenario behind the supersonic jets. What do you call it? I can't remember. The sonic boom. Have you heard about the sonic boom? It's the same thing. So it is moving out far further away. These are getting far away from one another. Okay. So you are supposed to know only the.
What do they test?
Huh?
How do they ask like questions on that?
We'll see. I have actually no idea about that. Sometimes they may ask questions like this. Now read this. When the sound source and observer are moving towards each other, that means we know a frequency increases. Velocity is constant. When frequency increases, lambda decreases. So there is a shift towards the higher frequencies, and the lambdas, they get closed. Is closed. And when they move away from one another, there is a shift towards the lower side. The frequencies decreases. So they might ask something like that. So it will now. You are stationary and the source is coming to you. Now by experience you know the frequency is increasing. Assume that the source is stationary and you are moving towards the source. Still when you get closer the frequency increases. So it is the same. The frequency will increase. I am stationary and the source is coming towards me, the frequency increases. And now the source is stationary and I am moving towards the source. Still we are getting closer to one another, frequency increases. So your questions will be mostly based on that. And sometimes you might have to give some examples. Okay, any questions? And questions, there is a very, I don't even remember the equation. Very complicated equation that you have for the Doppler's effect. When you know the velocities and the frequencies of one, you can obviously find the frequency of the other. So it's just a matter of substituting the values. But the equation is difficult, but it's not, you're not supposed to do that. Okay?
Just do the problems that.
Yes. I think we did almost all the questions except for
like
1 or 2.
5, yeah.
Yes. So do them and you will also get a homework assignment. I will come a little bit early, about 15 minutes early next time.
Yeah, I'll come on.
And please, you said that you had some questions.
Yeah,
Bring them, yeah. Take your note.
Wait, do you want this? I finished it.
Mm-hmm.
I finished the homework.
Okay. Oh, you got this too. So actually, these should be maybe due to
User errors,
errors. So this is obviously correct.